Hi everybody, this is Dr. Nigro here with another Chem Calculations screencast. This one's going to look at my favorite subject, which is stoichiometry, but we're going to look at it this time with gases involved and determining volumes of gases that are being produced or used rather than starting with grams or particles. So it adds an extra layer to what we need to be doing. I'm just going to use a general reaction as a way to illustrate what's going on. I'm just going to have some substance A. I'm going to have it react with an aqueous solution. I'll do a single replacement reaction while I'll form a new substance that's going to be a gas and then a new aqueous solution. All right, when we do stoichiometry calculations and gases are involved, you need to pay attention to the conditions. You are either going to be at STP, which means standard temperature and pressure, or you're not. If you are at STP, you can use molar volume as part of your conversions. If you're not at STP, you cannot. So you have to pay attention to whether you are at STP. All right, so let's start with that idea of at STP. So that means your pressure is 1 atmosphere and your temperature is 0 degrees Celsius. All right, so if I had the volume of A and I was trying to determine how much of B could be produced, I don't have a direct way to make that happen. So similar to our other stoichiometry calculations, our first step is going to be to convert volume of A to moles of A. Once we know moles of A, we can go to moles of B, and then we'll be able to convert to volume of B. So the question is, how do we do that? All right, if I want to go from volume of a gas to moles of a gas, I'm at STP conditions, then I can use my molar volume equality to make that happen. All right, so remember that 1 mole of a gas at STP is going to be equal to 22.4 liters of volume. All right, but the key here, at STP. I almost wish we didn't teach molar volume, because as soon as we do, every calculation, you want to use molar volume, but you only use it if you're at STP. All right, now once I've converted to moles, that's just going to be my mole ratio step, and then moles of B to volume of B, again, I'm going to use molar volume here again. Okay, now what if you're not at STP? So let's say instead we have non-STP conditions. All right, so you read the problem and basically it tells you that your pressure is something other than 1 atmosphere and or your temperature is something other than 0 degrees Celsius. All right, so let's say we want to do the same thing. We have the volume of A, we're trying to calculate the volume of B that will be produced. So the steps are the same. We want to convert from volume of A to moles of A, and then convert from moles of A to moles of B, and then we'll go to volume. The difference here is the first step and the last step. We cannot use molar volume because we are not under standard temperature and pressure conditions. So instead, we're going to use the ideal gas law, where P times V equals N times R times T. We're going to start with our volume and calculate the moles. So our unknown here is going to be N. That's what we're going to be looking for. We'll then use our mole ratio to go from moles of A to moles of B. And then on the other side, we're going to use the ideal gas law again. All right, this time, however, we'll know N and we'll be solving for V. All right, so when you're under non-STP conditions, it is a little more complicated because you have to use the ideal gas law. All right, I want to make a mention here. I'm saying that we're going to find volume of B, but we could start with volume of A and find grams of B, or we could start with volume of A and find particles of B, or we could start with grams of A and find volume of B. So we can mix and match all our other stoichiometry conversion factors that we already know how to use. We're just adding in a new layer. All right. We could also calculate the pressure of the gas at the end if we wanted. All right. We'd use PV equals nRT, just like we said before. We'd know this and that we would solve for P. All right, but that's going to be somewhat dependent on the problem. All right, so let's slide down and put it to work. All right, so we're going to try this problem. So this problem, we have a 12.5 gram sample of magnesium metal, and it's added to a sample of hydrochloric acid. If the reaction was run under STP conditions, what volume of the gaseous product was produced? All right, so as with any stoichiometry problem, we need a reaction, and then we need to make sure it is balanced. All right, so we're going to start with what we've been given. We've got magnesium. I'm just going to assume it's a solid. All right, and it's reacting with hydrochloric acid, which is going to be an aqueous solution. So this is a single replacement reaction. Magnesium is more reactive than hydrogen, so it will replace it, and we're going to get hydrogen gas as one of our products. and then magnesium chloride will be the other. Now, magnesium chloride is soluble, so it will be aqueous. We check for balancing. Everything looks good, except we need 2 HCl molecules. All right, so what have we been given? We've got 12.5 grams of the magnesium, and we're asked to find the volume, so I'll just put a liter here, of one of our products. It said the gaseous product, and the gaseous product is going to be the hydrogen gas. All right, we are under STP conditions, so that means that we are able to convert over using molar volume. So that's great, because that's going to make things a little bit easier. All right, so we'll start with our 12.5 grams of magnesium. And our first step is going to be to convert to moles. So we'll need our molar mass. So 1 mole of magnesium has a molar mass of 24.31 grams. So that should look familiar. That's going to cancel our magnesium. We're going to move next from moles of magnesium to moles of H2 using our mole ratio. And if we look at our coefficients, 1 mole of magnesium produces 1 mole of H2 gas. And that should also look familiar. And that'll cancel our moles of magnesium. It's our last step that's going to be new. Since we're under STP conditions, I know that 1 mole of any gas, in this case H2, occupies 22.4 liters worth of space. So that's going to let us cancel the moles, and it's going to leave us with units of liters, which is what we're looking for since the problem asks for volume. If we multiply across and then divide by the bottom, we should get 11.5 here. All right, so I want to point out each step here. This is a step we should be familiar with. That's our molar mass step. This second step is also one we should be familiar with. This is our mole ratio, not molar ratio. I guess you could call it that. And then this is our new step, molar volume. All right, and again, that is only possible because the problem told us that we were under STP conditions. All right, so let's try one when we're not under STP conditions. So number 2, a 50-gram sample of propane gas combusts with 500 milliliters of oxygen gas. If reaction conditions were 0.85 atmospheres and 35 degrees Celsius, what volume of carbon dioxide was produced? All right, so again, we need a reaction. So it says combust, so this is going to be a combustion reaction. So C3H8 is propane, and then it's going to react with oxygen gas, and we know that all combustion reactions produce carbon dioxide gas and water vapor. All right, we're going to check for balancing. We have 3 carbons on the reactant side, so I'll need 3 CO2s, 8 hydrogens on the reactant side, so I'll need 4 waters. That's going to give me 10 oxygens on the product side, so 5 O2 molecules. All right, now let's list what we've been given. We've got 50 grams of C3H8, sorry, my 5. And then we've got 500 milliliters of O2, and we're asked, well, what volume of CO2 is produced? Now, hopefully, you look at this and you're like, uh-oh, I have an amount for not one reactant, but both. So we're going to need to calculate how many liters that 500 mils of O2 will produce and how many liters that 50 grams of C3H8 will produce. So in other words, we have a limiting reactant problem here. All right, so don't forget, everything that we've learned before about stoichiometry is still present. We don't get to forget about limiting reactants. We should still remember what percent yield is. All right, we're just adding in this layer of having gases. All right, so let's start with our propane. So we have 50 grams of C3H8, and we need to convert that first to moles. So 1 mole of C3H8 has a mass of, and I'm going to get out my calculator, 32.1 grams of C3H8. Right now we're going to convert to moles of CO2. And according to our balanced reaction, 1 mole of C3H8 will produce 3 moles of CO2. All right, now I'm going to stop here because I'm going to determine which produces the least, and then I will finish it up. All right, so I'm going to cancel the moles, cancel the grams, and I'm going to find that I produce 4.69 moles of CO2. All right, but we're not done. We need to check on our volume of O2 gas. Now, because I'm not at STP, I need to use that volume, that 500 milliliters, and I need to convert that to moles of O2 using the ideal gas law. All right, so P times V equals N times R times T. All right, the pressure is given in the problem as 0.85 atmospheres. All right, I have 500 milliliters, but because of the units of R, I need to convert that to liters, so 0.5 liters. N is my unknown, 0.0821 atmospheres, liters, moles, Kelvin. And then I'm going to end with my temperature. It's 35 degrees Celsius, so 298 Kelvin. All right, calculate everything out, and I find that I have 0.017 moles of O2. All right, but I need to convert that to moles of CO2, so I'm going to put my mole ratio step right here. So 5 moles of O2 will produce 3 moles of CO2. So the moles are going to cancel. And I'm going to find that I'm going to produce 0.0101 moles of CO2. Well, that's really small, and that is by far the least. So here's my limiting reactant. So O2 limits this reaction, which means that it does not matter about the 4.69. That is done. All right, so I need to convert this into a volume. Again, not at STP, so I'm going to have to use the ideal gas law again. P times V equals N times R times T, but this time I'm going to be looking for volume. All right, so the pressure is the same, 0.85 atms. The volume is unknown, 0.0101 moles. All right, now I'm running out of room, so I'm not going to put the unit for R, but you should. It's good practice. All right, and then 298 Kelvin. So all three of those are multiplied together. I just ran out of room. So the volume of CO2 that's going to get produced by this amount of O2 is 0.300 liters or 300 milliliters. All right, again, the problem doesn't specify a unit, so I just leave it in liters. Okay, so you can see it a little bit more complicated, but it's not anything you guys can't handle. It's just using the ideal gas law. You just need to recognize when you need to use it. If you have a gas and you're trying to convert to something else, you're going to use the ideal gas law at the beginning to find N. All right. If you have a gas as a product or something else and you're trying to convert to volume, then you use the ideal gas law and find V. Okay. All right. Hope that helps.